The first talk is by Eviatar Bach from the University of Reading, who's going to be talking about learning probabilistic filters for data assimilation.
Thank you. Thank you very much for to the organizers for inviting me. So I'll be talking about this topic of data assimilation, which was touched a bit on yesterday talks, but this is going to be maybe a bit more of a mathematical talk than some of the previous ones, but I hope it's it's ultimately we're trying to do move to applications, so I hope it'll still be instructive. So just to advertise, we have these lecture notes on machine learning for inverse problems in data assimilation. We're going to publish this as a book next year. So this is with Andrew Stewart, Ricardo Baptista, and Daniel Sanz-Alonso. We just put up a new draft a couple of weeks ago. And a lot of the kind of mathematical foundations for the things that I'll be talking about are in here. So we go over Bayesian inference, variational inference, learning priors, learning transports from priors to posteriors, and then we also we have in the data assimilation we have variational inference for data assimilation, learning a model using data assimilation. We have learning filters themselves, and that's really what I'll be touching on in this talk. So just what is data assimilation to start off? So the point of data assimilation is to estimate the state of a dynamical system using a model forecast, often a physics-based model, and then noisy partial observations. So we have this data assimilation cycle. We have a true state of the dynamical, a true trajectory of the dynamical system. In this case, I'm showing in with this black line. And then at regular times, we have observations come in that I'm showing with these blue stars. And at each time, we're doing a forecast. And in general, this will be a probabilistic forecast. I'll talk more about that later. We have the observation, and we want to combine the forecast with the observation to come up with what we call the analysis, which is the updated estimate of the state given the observations. And then we use that analysis to initialize the next forecast. So data assimilation is really indispensable for chaotic systems, such as the atmosphere. So here I'm showing the Lorenz 63 model, which is a classic example of a chaotic system. On the left here, I'm showing two trajectories of the system that start off very close together in the red and the green, and you can see that they very quickly diverge. Because it's a chaotic system, we have exponential sensitivity to initial conditions. Whereas with data assimilation, I'm showing here in the blue, I'm assimilating into the model trajectory observations, and now you can see that they stay close together. The model trajectory stays close to the true trajectory. So this is really essential for numerical weather prediction. This is done in all operational centers, and it's also important in many other fields. So just some notation. We have a dynamical system that I'll denote this way. So we have this V dagger, that's the state of our system, and that's evolving forward in time. This is the time index J, using dynamical model psi, and we also allow for some model noise. And then we have some observations that are given as follows. so we apply an observation operator to the state and add some noise. So in general, the observation operator will select part of the state, and they'll be like partial and indirect they can be partial and indirect observations. And then I'll use this notation capital Yj as the accumulated observations from time 1 up to time little j. Okay, and then what we'd like to do is estimate this, what we call the filtering distribution. So this is the probability of the state given all the past observations. Sorry, I didn't write it here. Yeah, so we want the probability of Vj given given Yj, that's pi j, which is the filtering distribution. And to get to the filtering distribution at the next time, we follow 2 steps. One is a prediction step, and one is an analysis step. So in the prediction step, we're propagating forward our probability distribution under the dynamical model. In the analysis step, we're incorporating the observations into that forecasted distribution. And these are probability distributions. So P and A are infinite dimensional operators. P is a linear operator, but A is a nonlinear operator, which is where a lot of the difficulty in data assimilation comes in. So what does this A operator do? It's actually Bayesian. It performs a Bayesian inference. So essentially what it does is take the prior, which, remember, we take to be the last forecast distribution, multiplies it by the observation likelihood, which we've defined, and then normalizes. So this is actually just an application of Bayes' theorem, with the prior being the last forecast distribution. So this is the exact solution to the data assimilation problem, if you will, the probabilistic one. But in general, we can't evaluate this. This normalizing constant in particular is an extremely high dimensional integral. So, for example, in typical numerical weather prediction settings, you might think that this is that d is on the order of 10 to the 8th, right? So we can't do this. Explicitly. And so we don't typically have closed form filters for nonlinear systems. The dimensionality is huge, so we can't use approaches such as particle filters, which are common in other fields. The forward model is too expensive to run methods such as Markov chain Monte Carlo. We can only afford, on the order of 100 model evaluations at most, really. So we need methods that work for high-dimensional chaotic systems and require few model evaluations. And we want uncertainty quantification, since chaos leads us to many possible realizations if we have any uncertainty in the initial conditions. Okay, so I'll be talking about ensemble methods. And what these do is approximate the filtering distribution with an ensemble of particles. So we'll have this sum of Dirac delta functions where we assume each of these particles are approximately drawn from the filtering distribution. And I'll write down what the update is to get that, but essentially what you can see, this is just showing an ensemble in this Toy-Lorentz example from before. We can estimate the time varying uncertainty in the system using this ensemble. So Why is this attractive? It's feasible for high-dimensional systems. It's a derivative-free method, and it has this flow-dependent uncertainty that we care about. So I won't go into much detail, but essentially the ensemble Kalman filter works as follows. We have an ensemble of particles, capital N particles, and they evolve according to this algorithm. In the forecast step, we apply the dynamical model to each of the particles, and in the analysis step, we update the forecasted ensemble with the observations. So we're essentially nudging towards the observations using this Kalman gain K. So if you're familiar with the regular Kalman filter, this might look familiar. The difference is that here we're computing the Kalman gain based on covariances that are computed from the ensemble itself. So it's a type of Monte Carlo method. So we have this cross covariance between the particles in the state space and the ones mapped into the observation space, and then we also have the covariance of the particles in the observation space. I'll just say that we generally need some tricks to make the ensemble Kalman filter work in high-dimensional settings. One is inflation. In general, there will be a systematic underestimation of the covariance matrices due to sampling error. So we need to inflate those covariance matrices. Another is localization, where we only allow observations to inform nearby states, essentially. So if we have a physical problem, we'll only allow those observations that are nearby, in some sense, to influence our states. An issue with the ensemble Kalman filter is it's not consistent in the Bayesian setting. So we know that even if we increase the number of ensemble members to infinity, we won't recover the true posterior. And this is part of the motivation for what I'll talk about next, which is learning filters. So first I'll talk about some work we did on learning filters using variational inference. This is in a preprint with Enoch Luck. He did a lot of the numerical experiments, and Andrew Stewart and Ricardo Baptista. So the aim of probabilistic data assimilation, as I've described it, is to estimate this analysis step. But existing filters that are used in practice are very powerful, but they're suboptimal and involve numerous tuning parameters. So here we consider learning the data. We consider learning the analysis step in the data assimilation process to get improved filters. And we can do this, we can apply this in learning tuning parameters in existing filtering methods, or we can actually learn new filtering methods closer to optimality. So I'll show some results on that later. Okay, so we want to learn a probabilistic filter. We don't want something that just minimizes the root mean squared error or something like this, which has been done before. So we need a cost function that's minimized only at the true filtering distribution. And we'll do that using variational inference. To do so, we'll use the Kullback-Leibler divergence. So some of you may be familiar with this, but essentially it's a kind of measure of distance between probability distributions. It's not a true distance because it's not symmetric. It's a divergence, but you can kind of think of it as measuring a discrepancy between two probability distributions. And then we'll use something that we call the variational formulation of Bayes' theorem, which says the following. If we have this cost function that's a function of probability distribution Q. And we take the KL divergence between Q and some prior, P of U. And then we have this expected log likelihood. Then the minimizer of this cost function over the set of all probability distributions will be the Bayesian posterior. So this is a way to turn the Bayesian inference problem into an optimization problem. So you can see this. This is a term that's measuring closeness to the prior, and this is measuring closeness to the observations. So it's a trade-off between those two things. But it's nice because this is an equivalent formulation of Bayes' theorem in an optimization sense. Now, how do we apply this to the filtering setting? So if you remember, I said that the analysis step is an application of Bayes' theorem at every time. So we can just directly use variational inference to transform this analysis step into an optimization problem. So now we say that the filtering distribution at time j plus 1 is the minimizer of this cost function, which is taking the KL divergence between Q and the last forecast distribution, and then this expected log likelihood, which is measuring the closeness to the observations at time j plus 1. Of course, we can't optimize over this set of all possible probability distributions, so we want to look in a parameterized class. So the way we'll do this is we'll say we have an approximate analysis map. We don't have this exact analysis map, so we'll parameterize it by some theta. And that defines a class of approximate filters that we can optimize over. So you can think of these theta as a tuning parameter in an existing filtering method. So for example, in an ensemble common filter, or it could be something more general, right? It could be neural network parameters, which I'll give some examples of later. But this is so this is a general framework to capture that. Yes, and then we can do this recursively, and then we have this sum of cost functions at each time. And if we can use the automatic differentiation through a parameterized filter, then we can try to find the best parameters theta that minimize this cost function. We'll get as close as possible, assuming we can do this minimization to the true filter within our class. And the important thing is that this analysis operator is actually, the true analysis operator is constant in time if our observation likelihood is not changing. So we can do this learning over some time, and this is a type of amortized inference. So we spend a lot of effort learning this, but then we can use it in the future very cheaply once we've learned it. Okay, and we can also do this at each step, and that's what we call the online method as opposed to the offline method where we're amortizing. So I'll show some numerical examples of this. The first thing is we learn a fixed gain. So this is a very simple example. We're just learning a fixed gain for a linear dynamical system. The reason why we looked at this first is that we know what the true solution is, so we can compare against it. So we have the analytical solution, which is the steady state. It's called steady state common gain. Here we have the error as a function of gradient descent iterations when we're comparing to the true steady state gain, as well as prediction error. So we seem to be doing pretty well. This is the true analytical gain, and this is what we learn, and they look visually indistinguishable. They're very close. So we can do this. We can also do this in a partially observed case, we can do this using the online method. Now I'll show an application to a nonlinear system. So we have a chaotic system called a Lorentz 96 system, and this is very often used in data assimilation studies. So essentially, it's an ODE that's chaotic and is representing the dynamics of the mid-latitude atmosphere. And we also use the Kuromoto-Sivashinsky model. This is a one-dimensional chaotic PDE that comes from flame propagation. Okay, so now we learn a gain for this nonlinear system. And this is what we find. This is the gains produced by a different method called the extended Kalman filter. And we essentially learn a lot of common features. So we have this banded structure. We have the symmetry and yeah, so quite a similar structure. So that's just to show that we can learn what existing methods are doing. We can also tune methods like the ensemble Kalman filter. So here we tune these inflation and localization parameters, and we can have this cost landscape where we can see, as a function of ensemble size, what are the optimal values of these parameters in a probabilistic sense. And as far as we know, that this is all new. And we recover some things that are kind of people have known in practice, but now we can verify it using this closeness to the true filtering distribution. And we did this also for the Kuromoto-Sivashinsky equation. I'll just go, please, so I can show some of the more exciting results. But I'll just mention that this variational inference method has issues in high-dimensional settings. So we have a different idea, which is to use strictly proper scoring rules, which is something that we've started to do. So a scoring rule is a way of assigning a score to a probabilistic forecast with an observed sample. And we have this concept of propriety and strict propriety, which essentially says a proper scoring rule is one that's minimized in expectation at the true distribution from which your data came. Strictly proper is when the equality holds if and only if the distribution from which you if and only if you predict the actual true distribution from which your data came. And then we could set up a cost function that's based on these strictly proper scoring rules. And these are amenable to ensemble approximations. So that's a way that we can scale some of these ideas to higher dimensional settings. I'll just talk briefly about this other work, which is about learning enhanced ensemble filters. Again, this is in preprint, and this is also with Bohan Chen, who did a lot of the, well, he did the numerical experiments, and also Eduardo Calvello. So here we're actually taking a step back and going back to deterministic evaluation. So here we're using a state estimation loss function rather than a probabilistic one. And what we do is we want to learn a correction to the ensemble Kalman filter that improves its performance. So we do that by learning a correction to the ensemble Kalman filter gain. So we have this gain k theta, we have these gain matrices here, these matrices here that form a part of the gain, and within these we have these learnable functions w hat and z hat, and these are outputs of a neural network that takes in that takes in as input the ensemble, the observation, and our each individual ensemble member, as well as its value in the observation space. So we're really learning a mapping that's taking a probability measure as input, and outputting outputting a correction to an existing method, and we call this a measure neural mapping. There's a lot of more mathematical discussion in the paper, but I'll show some results for this. The nice thing about this is we used so this neural network is what's called a set transformer. This is a permutation invariant neural network. So essentially, since we're giving as input an ensemble, we want this output to be invariant to permutations of the input ensemble, because any permutations are not significant. So we did this using a set transformer. This also has the property of being able to take invariant input sizes. So this means we can train at one ensemble size and deploy at another size, which is also a nice property. And then we also learned inflation and localization parameters based on ensemble size. So we use those to fine tune. Okay, so here are the results. So I'm showing here root mean squared error for different filtering methods. This is again for the Lorenz 96 system, and this is ensemble size. And the important thing to note, so blue is our method here, and kind of the best competitor is the LETKF. So like it can a leading data assimilation method called the local ensemble transform common filter. So we can actually see that we're doing quite a bit better, especially at the smaller ensemble sizes. And we outperform all of the other methods as well, so we have significant improvements compared to leading methods. We also have the Kuramoto-Sivashinsky equation, and again we see very significant improvements compared to leading methods with our learned filter. Okay, so just to conclude, we can use variational inference to learn probabilistic filters for data assimilation, as well as setting tuning parameters, and do this in a Bayesian way. We showed examples of applying this method to learning gains for filtering linear and nonlinear dynamical systems, as well as inflation and localization parameters in an ensemble common filter. Then I showed some results using a deterministic loss function and showed that we can improve on state-of-the-art filtering methods by learning a correction to the ensemble common filter using a permutation invariant neural network. Future work is we want to learn general filters that get as close as possible to the true Bayesian filter using these probabilistic loss functions that I discussed, using strictly proper scoring rules, and we're also looking at issues of scaling to very high-dimensional systems. Another question is, how do we deal with model error? This framework has assumed that we have access to the true model, or a good approximation of the true model. So that's another issue. Yeah, that's it. Thank you.